Good afternoon. This is a short introduction to the basics of radio-based signaling, which would would be would be good point to start with. In this presentation, we shall not discuss any major technical issues, but only introduce the way the radio-based signaling works to those who are new to this subject. So, the contents of this presentation would be very basic, and the format of this presentation is I shall first provide you with the presentation, and then if you have any questions, you can raise them at the end of the meeting. So, I will start with the way fundamental signaling systems offers safety. In the conventional signaling system, safety is achieved by dividing the railway network into tracks, which are generally called track sections. So, a railway network can be considered a set of track sections, and if you try to present them as a set, it is a set of track sections, say 1, 2, and so on. Now, a railway network will always be a set of finite number of track sections, as the railway network is a closed one, and vehicles belonging to a railway network has to be continuously be on any one of the track sections belonging to the network. Now, in fundamentally in conventional signaling, the the control equipment basically identifies portions of tracks which are free for use for other for any rail vehicle before authorizing a rail vehicle to move into that portion of the track. Yeah, if you look at the components of a if you look at the components of a railway network in the conventional signaling, as I said before, it is a set of track sections. It forms a set of track sections, and the control system, which is the safe train control system, which you see on the screen, ensures that any train, any rail vehicle, which you see on the right hand side of this slide, continues to remain safe on the network by the intervention of the safe train control system. A safe train system is connected to a train management system to control the trains, which basically authorizes or selects the sections into which the trains can go in. This functionality is not well safe or safe by itself, but it is it is processed through the safe train control system, which will only allow the train to move into track sections which are safe for a train to move into. Now, railway network runs several rail vehicles, obviously, because that is the main purpose. Now, each rail vehicle requires to remain stopped on a train section or remain on a stop track section unless it is authorized to move to another adjacent track section. So if we go to the previous slide, this train cannot move into this section unless the authority is provided through this signal and which comes from the safe train control system. Now, such movement is authorized when authorized by the train management system, as we have seen before, and then is processed by the train control system, and only if it is considered safe, it moves into it. And this authority is determined to be safe only if there are no other rail vehicle occupying this track section to the track section to which the authorization is given to the rail vehicle moving into it. Now, to explain this further, consider the example here where we have got two trains which are controlled by this system, and the train one is waiting to be let into the train's track section 2, which is occupied by train 2, and it will not become clear till train 2 is or moving or moves on to track section 3. Now, when the train moves to track section 3, the train 2 that is, the train number 1 will be now authorized to move into the next track section. So, these are all controlled through color light signals which tell the trains to go ahead, past it or not. Now, when we move on to the radio based railway signaling, we are actually not dealing with anything fundamentally different. The basic control is still applied to the same railway network, which has got track sections which are defined in it. Now, unlike the conventional signaling, the track section associated with a train need not be fixed. So that is an advantage that a radio-based railway signal provides over a normal railway signal. Now, however, we shall assume that the sections are fixed rather than moving with the train for the purpose of this presentation. It does not make a lot of difference to the way control system exercises the controls, but we should remember that the track section, which in a radio control signal is not or not necessarily need to be of a fixed type. It can move along with the train, and that is the advantage of the radio based signaling. And where that method is used, it is called a moving block signaling rather than a fixed block signaling. Now, the safety of a train in a radio-based signaling is very similar to conventional signaling with minor differences. Now, there is a information provided to the onboard display advising the driver on board about the distance that is safe enough for the train to travel, and this information is continuously available unlike a conventional signal. Once in a conventional signal, once you have passed a signal, the train is no longer provided with any additional information about the section it is moving in or ahead of it. Whereas in the case of radio signaling, this information is continuously available, and if there is an emergency, in fact, it can even be reduced to the distance that it can safely travel can be reduced. On the go, though, can may not be possible to ensure because this momentum of the train may not allow the emergency situation to fully be deflected, but still there is an additional opportunity of controlling a train which finds in hazard suddenly cropping up. Now, uh, uh, Consider the more generalized diagram of a radio-based signaling, where each of the train are provided with radios. They are actually radios which work to the specification known as GSMR, and the train control system is continuously aware of the position of each and every train to a degree because there are some errors which are inherent when evaluating the position of a train, and therefore the control system can never be 100% sure of the exact position of a train. The the train has a reasonable level of accuracy of localization, and therefore it can be ensured that a train in rear of it and traveling towards it will not come so close and actually collide with it. This is ensured by ensuring, like in this picture, that the train B, which is traveling in rear of train A, is always kept at a safe distance from the train A based on the location of train A as is known to the radio control system. Now, there are errors which are known, the errors which are obviously because of the fact that train position is basically localized, as we shall see shortly, based on the train travels from certain known locations along the track, which are marked by certain equipment, and this distance that a train moves is not 100% accurate because the important item it relies upon is the odometer. The odometer on the train will never reflect the true distance traveled because the odometer is based on the number of turns the wheels undergo, and if there are any slips and unideal unideal movement, that is the train moves but the wheel does not move as much, the errors will be there. So when the safe distance to which a train in rear can be allowed to go is computed, the train will be provided with a distance to go information from which the error of localization of the train in advance is subtracted. So it will never happen that train B will actually collide with train A because the errors are always done in this fail-safe manner. Now, as we have just discussed, the safety of trains in the radio-based signaling requires accurate localization of providing information to the onboard display, which so accurate localization of the distances. Now, how do we ensure this? This is ensured by providing some fixed reference points along the track. Now, one of the most common ways of doing it in the radio wave signaling system is by provision of equipment called balises. The balises are provided at known fixed locations along the track, which is known to the RBC. So, when the train moves over a valleys, the balise takes the information. Sorry, the balise is powered by the train, and the information in the balise via the locomotive via the train is sent to the RBC. Now, this proves to the RBC that that particular train has now come and moved over the valleys. Now, because the valleys is at a known place, the odometer error at that point is considered and can be considered as zero because there is an absolute localization of the train. But as it moves towards the next valleys in advance, as here, this one from the one in the rear, the odometer reading is the source of updating the localized information of the train. As we mentioned, this cannot be and will not be accurate, and therefore the distance from the valleys will not be exactly equal to what it is actually. And for safety, again, the train is assumed to be localized by an amount equal to the error in rear of the train. Now, the mechanism by which it works is by means of a antenna in below the underframe. Now, the antenna, when it passes over the bellies, extracts information from the bellies using radio signals. The information provided identifies the bellies, and this information is relayed by the train to the control system, which then is able to determine accurately the position of the train. This is where the odometer error is therefore is corrected and is considered as zero. And as the train moves, the odometer information of the trains becomes available to the control as well as to the onboard equipment to determine how much the train will be able to travel safely based on the position information of the last traverse valleys. This last traverse valleys is called the LRBG, last reference valleys group, and the entire safety of the system is actually based on the distance a train is allowed to move from the LRBG. This is a extract from the subset 0 to 6, where it explains how the LRBG is used to localize a train and ensure that no track section is occupied by a train by two trains which have been already localized using the LRBG. For safety of train operations, where radio control is used, every train registered on the radio control system is kept updated with a safe distance it can progress. Here, as we see, the safe distance from the LRBG is up to the next marker board where a fixed block is used. As we said, we can also use another train that is the moving block, then it would be allowed to move to based on the distance of the previous train from the LRBG and or so this way it will always ensure that the two train or no train will occupy the same distance. Now, as I mentioned, the last reference values group is who is the reference for the control of the train. Now, how does the safety of a train is maintained? Now, as I mentioned, we have considered only one aspect in the previous part of the presentation, that is where there is a obstruction and the train is moved to a particular distance in rear of that obstruction. So this is a target. This is known as a target, and there are three types of main targets. The most important target is the end of authority. That is a point which marks the absolute maximum distance the train can travel without being without any hazard. Generally, immediately after the end of every end of authority, there is a point known as a danger point, and the target, when we say the distance that a train is allowed to travel, is based around that end of authority. Now, that end of authority can be preceded by what is known as a limit of authority. Now, the limit of authority is a point where a train may be given a target speed which is not zero. So, it is this is necessary because you may have a situation where you want to see that the train is approaching the end of authority at a relatively comfortable speed to allow it normally to stop at the end of authority, yet not being affected by the errors to such a degree that a train can never reach it. So you can have a point from to the edge to which the train will move at a low speed, low enough to control the train thereafter to come to be brought to a stop. You can also improve the running if you add a overlap to the end of authority that is known as the supervised location. So where you provide a supervised location, the train can move at a comfortable speed when it is very near to the end of authority at what is called a release speed, and because of the finite release speed, the train is able to come to a stop very close to the end of authority. Where there is no supervised location, the ability to automatically bring a train very close to the end of authority is not there, is not is actually impossible, and therefore if there is no overlap, the train will not be able to come very accurately to a stopping point because the safety will not allow it to go to that close a point to the danger point. Now, that is target monitoring. That is, a train always monitors the target point to which it will be allowed to travel. However, that is not sufficient because a train may be traveling at a speed higher than what will allow a comfortable uh, operation of the train, and also that it can be properly brought to a stop before an actual hazard happens. So, a train generally monitors a few speeds. The system, that is the onboard system, continues to monitor a set of speeds which will be able to ensure that the target points are easily achieved. Now, generally, the three kind of speeds are monitored. One is the ceiling speed, that is this running speed, you can say the line speed, so that which will never be exceeded by the train. Now, as long as the train is far away from the end of authority, this is the main control available to the train speed. The following that is the speed which is the target speed, that is, if there is a point where there is a stopping point defined which is a limit of authority, A target speed of non-zero target speed is generally specified, and it moves it in such a manner that if it comes to the limit of authority, it will be traveling at that target speed. Now, the target speed monitoring is therefore available after the ceiling speed monitoring. Thereafter, the train monitors what is known as the release speed. The release speed ensures that a train will not go beyond the end of authority under any condition. Where the end of authority is not having an overlap, the release speed is lower than what it can be provided when there is an overlap, because of the general manner in which train can be controlled to be brought to an absolute safe stop at the end of authority. Now, before I end, I'll quickly go through the special case of a train which is moving from a conventional signaling area to radio based signaling and vice versa. Now, the managing of entry into an exit of a train between conventional signaling and radio based signaling has to be done in such a manner that minimum there are minimum uh, conflicts between the two, and a train can smoothly move from one type of signaling system to the other. So I have given a situation or drawn a situation in this slide where a train in the conventional signaling is now entering the radio based signaling territory, and as it moves it should ensure that at the marker board, this marker board signifies the border of the two territories, and as it moves it should not happen that the train has a conflict between the two systems. Now, how can the conflict happen? We want that when a train from a conventional signal is entering into a territory or which is controlled by radio signaling, it should approach this border at a speed which is at a speed which is sufficient to ensure that when it is already in the territory, in the radio based signaling territory, the path is available for, sufficiently in advance of the border, and the train can then be safely brought to a stop before any hazard in the radio based signaling territory. Now, to achieve this smoothly, there are two things we have to also keep in mind, that the train that is coming from the conventional signaling territory, is is advised of the state of the territory, the network in ahead of the border, and therefore it has to be first registered well in advance to the radio based signaling territory, and then it has to also start a communication session with the radio based signaling control system. Thereafter, the actual control of the train happens. So these three valleys in rear has to be the minimum. It's not minimum, but it is it is most desirable. And by the time it reaches the aspect control valleys, it should already be in proper communication with the radio based control system, and it the radio based control system can then be in a position to arrange entry of this train as soon as possible into the radio based signaling territory. Now, it is to be understood that there is no benefit in doing the get in setting the territory, setting the routes in the radio based signaling territory too much in advance of the train which is coming from the conventional signal territory, because it will cause loss of capacity. Yet at the same time, if the train is coming, it should not happen that by the time it reaches the border, even if even if the radio based signaling territory is ready to accept the train, the route cannot be set. So it should be ensured that the route setting of the transition border is taken up well in time to ensure that when the train reaches or sees signal 2, it is already available, and if it is free, then it should be able to show a green aspect and a travel right into the radio based signaling can go unhampered without any restriction to the train speed. At the same time, we need to ensure that there is a safety in the operations. So signal 2 will not show a proceed aspect or green aspect unless there is a safety to do so, and in such a case it can happen that the route setting will be delayed till it comes to a position where an unconditional setting of the route into the radio based signaling territory will be undertaken. When an unconditional route setting is undertaken, it the system it can happen that it never happens even when the train has reached signal 3, and the train will then be brought to a stop by the conventional signaling system. Remember that if this conventional signaling system do not have any train protection inbuilt, then the train can will have to be done by the driver intervention, and if he fails to do so, it can result in a mismatch and tripping as soon as it enters the radio based signaling territory. However, we assume that the driver of the conventional signaling system will have sufficient understanding to see that it brings the train to a halt at in rear of signal 3 if it is not safe to go in in advance of the border. The On the other side, if a train is coming into the conventional signaling territory from the ETCS system, it is desirable that the speed at which the train enters the conventional signaling territory is such that it will be brought at a stop in rear of the possible authority of that signal, a possible authority of the signal 3 on the other direction. So, when the train comes in from the radio based signaling territory, it is essential that first the speed at which it is allowed to cross the border is sufficient to ensure that it does not go past signal 3 or signal 4 if if it is not safe to do so. So the speed at the time it crosses should be sufficiently controlled to ensure this happening. Though if we we specify that unless both the ETCS territory first signal and the RCS, the conventional signal fast signaling is not clear, we will not allow the border to be crossed. The complications are sufficiently reduced. So this brings us to the end of this presentation. It was a very short presentation, mainly to introduce the basic concepts of how the signaling system performs in a radio based signaling to deliver safe control of trains. Now, if you have any questions, we are ready to take it. Else, we'll close this meeting for the day. All right, I would consider that there are no more questions to be answered in this session, and we'll close this meeting for the day. Thank you for joining.